Okay, as a quick reminder, what we're doing here is we're using some of the information that we've seen on the past couple pages to answer some questions we might be interested about. And as we go through this, I want to remind you that all this is based on box number 1. Okay, box number 1 is a really important box, and we're going to relate everything back to the things that are being said in this box. And so the next question here is telling us, or asking us, from the information given, let's figure out what quadrant we must be in, what quadrant t must be in. So if we know that tangent of t is positive, and we know sine of t is negative, that tells us something about the quadrants. Because we know, based on box 1, all right, this is all based on box 1, tangent is y over x, right, and sine is y. Okay, so let's write that down. So we know that tangent of t is y over x, okay, and if that's positive, then that means that both the x and the y value are positive, or they're both negative. And so this occurs in quadrant 1, where both the x and the y value are positive, and 3, where both the x and the y value are negative. Because if they're both negative, they cancel out and they become positive, right? And we know that sine is the y value, and if sine is negative, then the y value must be negative. And that occurs whenever we're below the x-axis. So that would be quadrants 3 and 4. And so based on this information, we take what's common to both of them. So the first one says we're either in quadrant 1 or 3. The second one says we're either 3 and 4. And so if we want both of them to be true, we take the one that's in common, and the one that's in common is 3. So in order for tangent to be positive and sine to be negative, we must be in quadrant 3. So if tangent is positive and sine is negative, then we must be in quadrant 3. I would encourage you to take a second and think about this one and see whether or not you get that one correct. Use the exact same logic and relate it back to box number 1. Pause the video now if you're going to give that a try. I strongly recommend you do that. I hope you gave that one a try. And so if we know cosine is negative, cosine is the x value. And if that's negative, we must be in quadrants 2 or 3. Those are the two places where the x values are negative. Cotangent is y divided by the x value. And if that's negative, that means that one of them needs to be positive and one needs to be negative. Right? The only way to divide two numbers and get a negative is if one of them is positive and one of them is negative. And so that happens in quadrant 2. Right? In quadrant 2, x is negative and y is positive. And quadrant 4. Because in quadrant 4, x is positive and y is negative. And so again, if we want both of these things to be true, we need to take the ones that are in common, and what's in common is quadrant 2. And so the answer to this would be cosine is negative and cotangent is negative in quadrant 2. But again, we related it back to box 1 by knowing what the values of those trig functions are in terms of x and y. If we can just relate it back to box 1, these problems really aren't terribly difficult. We're going to do a couple of similar ones on the next page. So let's switch over to the next page. On this page, we're being asked kind of similar questions, and we're going to use similar reasoning to answer them. So the first one, we're going to write the first expression in terms of the second if the terminal point is in the given quadrant. And so what this question says, if it says cosine t, comma sine t in quadrant 4, the instructions are we want to take cosine and write it in terms of sine, given that t is in quadrant 4. So t being in quadrant 4 is going to tell us something about the signs of these things. Okay? And so the way we want to think about these is we want to look at the identities in box number 5. And we want to look at ones that relate sine and cosine. We want this to say cosine equals something with sines. So we want to look at box number 5 and look at identities that relate cosine and sine. So that's what we're thinking about. Let me take out that box here. And so this is box number 5 that I'm talking about, this one right here. I didn't have it labeled, but I will label it now. Box number 5. This is all the identities, and this is how we can take one trig function and write it in terms of another. And so in this problem, we want to write cosine in terms of sine. And so I'm looking at these identities and thinking about what's a function that has cosine and sine in it. And when I'm looking through, there's only one that has just cosine and sine, and it's this one. Right? Take a second to convince yourself that none of the other functions have just cosine and sine in it. And so we want to use this identity, sine squared plus cosine squared equals 1. And so I'm going to write that down. So we know that sine squared plus cosine squared equals 1. Remember, this is a form of the unit circle. And what we want to do is we want to take that equation and solve for cosine. And so let's get cosine by itself. And so I'm going to subtract the sine over to the other side. And so I've almost got cosine by itself. I don't want cosine squared, I just want cosine. And so we take a square root, and when I take a square root, the square goes away on the left, and I get plus or minus on the right. Right, don't forget about the plus or minus. Now, this is where quadrant 4 comes in. If we're in quadrant 4, cosine is positive in quadrant 4. And we know cosine is positive in quadrant 4 because I'm relating it back to box number 1. Cosine are x values, and x values are positive in quadrant 4. And so, based on this, I know that cosine, which is the x value, is positive in quadrant 4. And so I'm going to use the positive version of this, not the negative. And so that means cosine equals the positive 1 minus sine squared inside a square root in quadrant 4. On the next one, we want to write sine in terms of secant. So we want to end up with something that says sine equals, and the other side of the page should be secant. And so when I'm looking at the identities, I'm trying to relate sine and secant. But as I'm looking through these, there isn't a function here that has just sine and secant in there. Right? Look at that. Secant, but this has cosine. Right? Sine, but it's cosecant. There's not an equation that relates the two of them. So I'm going to have to do this in 2 steps. What I'm going to do is I'm going to relate secant to cosine, and then we just related cosine to sine. So cosine is this in terms of sine. And so that's what I'm thinking from this one. So from that box, so from box number 5, we see that secant is 1 over cosine. And we just wrote cosine in terms of sine. And so we can take this thing that we just found and plug it in right here. Because that would then be secant equals something that only has sine in it. And so that would end up being the following. We'd get secant equals 1 over the square root of 1 minus sine squared. Now this is now an equation that relates secant and sine. But this is secant in terms of sine, and the problem is asking for sine in terms of secant. And so we want to take this equation and solve for sine. And so that's what I'm going to do. I'm going to take that equation and solve for sine. It's some algebra. It'll be some good algebra review. And so I'm going to start with this equation and solve for sine. So the first thing I'm going to do is I'm going to invert both sides. The other way to think about that is I'm going to cross multiply this thing. And so I'm going to invert both sides. So I'm going to flip both sides upside down. So this is like a secant over 1, right? And so I'm going to flip the secant over 1, and I'm going to flip the 1 over square root. I'm going to flip both sides. And we'll get 1 over secant equals square root of 1 minus sine squared. Now I want to get sine by itself, so I want to get rid of the square root here. And so the way you get rid of a square root is by squaring everything. So we square both sides, and we end up with 1 over secant squared equals 1 minus sine squared. I'm getting close to having sine by itself, so let's subtract the 1 over the other side and multiply by negative 1. So I'm going to do 2 steps. I'm going to subtract the 1 and multiply by negative 1. And so we'll end up with 1 minus 1 over secant squared equals positive sine squared. And now I take a square root to get rid of the square on the left, on the right side. And so we get that sine equals plus or minus 1, it should be 1 minus 1 over secant squared. We want to figure out which is it plus or is it minus, right? And so we're in quadrant 4, and quadrant 4 has y values that are negative, and so sine is negative there. And so the way I finish this one off is by realizing that sine are the y values, and those are negative in quadrant 4. And so that means my final answer is the negative version of that square root. So this is sine in terms of secant. Right? Sine's on one side of the equation, secant is by itself on the other side. Not by itself, but it's the only thing on the other side. Okay, great. These ones are a little bit tricky, and we'll see these later. Well, these come back into play when we start talking about trig identities, and so we will definitely see these later, and we'll come back and practice writing things in terms of each other again. The last piece of information on this page is just another kind of application of the things on the past few pages. And so the instructions here are to find the values of all 6 trig functions of t given the information that we're being told. And so in this problem, we're being told that cosine is minus 4/5 and that the terminal point is in quadrant 3. And so all we need to do to write the values of all 6 trig functions is we need some x and y point. And so this is telling us one of them. If we have both, we can just plug them into the formula. Cosine is telling us 1 because we know that cosine is the x value. And so this is telling us that cosine, which is the x value, is minus 4/5. So we have the x value already. So we already have the x. Now we just need to find the y. Now the y value comes in from the fact that we're on the unit circle. And so since we're on the unit circle, we know that x squared plus y squared equals 1. I'm just looking through my notes right now to show you that page. But this is from the very first page of the unit circle. If we're on the unit circle, which we always are when we're talking about trig, we know that x squared plus y squared equals 1. And so if we have an x value, we can find the y value based on that. And so that's what I'm going to do. So we know that x squared plus y squared is 1 because we're on the unit circle. And so I'm going to plug in this x value into here and then solve for y. And so we have minus 4/5 squared plus y squared equals 1. And now we just solve for y. And I will go ahead and do that. So when we square minus 4/5, we just square both the numbers. And so that's 16 over 25 plus y squared equals 1. Let's get y by itself. And so we want to subtract the 16 over 25 over to the other side. And when we do that subtraction, we get 9 over 25. And so then when we take a square root, we take a square root of both sides, and we get that y equals plus or minus square root of 9 over 25, which is plus or minus 3/5. And so this is our y value, but we need to pick one, plus or minus, and we see that we're in quadrant 3, and y values are negative in quadrant 3. And so since we're in quadrant 3, y values are negative, which means we take the negative 3/5. And so now we have an x value, minus 4/5. We have a y value, minus 3/5. And so we can use those two x and y values, and we can plug them into all 6 trig functions. And so that's what I'll do right here for the rest of this problem. So we know that sine is the y value, so that's minus 3/5. We know we already have cosine, right? Cosine is minus 4/5, so I'll skip that one. We have tangent. Tangent is the y divided by the x value. And so when we divide the two, we do minus 3/5 over minus 4/5. We flip the bottom fraction and multiply, and so we get minus 3/5 times minus 5/4. The 5's cancel and the negatives cancel, and we just get positive 3/4. Secant is the next one. And so secant of t is 1 over the x value. And so in this case, that's 1 over minus 4/5. And so again, we take the reciprocal of the bottom, and we get minus 5/4. Cosecant is the next one. Cosecant, we do 1 over y. And so that ends up being 1 over minus 3/5. So that's minus 5/3. And then finally, cotangent is x divided by y. So we do minus 4/5 over minus 3/5. I'm running out of room here, so I'm just going to jump to the conclusion. But we flip the bottom fraction and multiply it. The 5's end up canceling and the negatives end up canceling, and we get 4/3. And so just to summarize here, we were given a cosine value. We knew that that was the x. We plugged it into the equation x squared plus y squared equals 1 to find y. And then once we figured out what y was, we just plugged it into the equation from box number 1. Right? Just to be clear about that, all these formulas, 1 over x, x over y, all those things are coming from box number 1, which is a really important box. Right? It's got a lot of stars by it. We really want to make sure that we understand that box. So I would recommend you try this one yourself. Before you try it, maybe let me just point out that, we're being told that secant is 2 and that sine is negative. And so secant is 1 over x, and that's 2. And so we know that 1 over x is 2. And so this is an equation you could solve to find x. If you'd like to try that one on your own, and I strongly encourage you to do that, please pause the video now, and then I will finish going over it. So when we solve this equation for x, you multiply both sides of the equation by x. It cancels out on the right, and we get 1 equals 2x, and so that means 1/2 equals x. And so we have an x value. We plug that into the equation x squared plus y squared plus 1 equals 1, And so we put this into that x, and we get 1/2 squared plus y squared equals 1. and then we solve for y, just like the last problem. And so this is, I'll let you work out the details here, but you'll get y equals plus or minus square root of 3/4. Excuse me. Now, we're being told which one of these do we pick, plus or minus. Excuse me. So we're being told sign is negative, and sign is the y value. And so we have that sign is negative, and sign is the y value. And so we take the negative value then, and we use negative square root of 3/4, which is the same thing as negative square root of 3/2. Right, and so this is on the unit circle, 1/2 comma square root of 3/2. Right, that's the point associated with pi over 6. And so now we have an x value, we have a y value. I don't really have enough room, and so I'm just going to write down right here, you finish this problem by plugging in the values into the formulas. So using these x comma y values, we can plug them into the formulas in box number 1. Just like in the previous problem, you get all the values of all 6 trig functions at that point. All right, so what we're going to talk about today are graphing trig functions. Specifically, we'll talk about graphing sine and cosine today. We'll talk about graphing the other trig functions in a future section. Today we'll focus on sine and cosine. And just to give you a little preview of how this lesson is going to work, we're going to go through the next several pages, and this first page here is a reference page which is going to end up setting up what sine and cosine look like. Okay, we'll kind of get the general idea behind why those shapes, why these two graphs have those two shapes. The one on the top here is sine, the one on the bottom is cosine. We'll relate that back to the unit circle and try to understand how we can remember those shapes. And then what we're going to do is we're going to plot these transformations of these two graphs, I should say, just like we've done transformations for every other function we've graphed. The difference is with trig functions is they can get increasingly complicated. And so just looking ahead on the next couple pages, once we have a good idea from this page about what sine and cosine look like, we will add some complexity to them by adding some numbers and multiplying. Okay, this is the next page. On the following page, we will then add another complexity by adding a k inside. And then finally on the last page, we'll add a third complexity, which are shifts. And so notice that on each subsequent page, we add another level of complexity to the problem. But just know that we're just doing transformations like we've done transformations with everything else, okay? And again, with the first form, we'll just talk about vertical and horizontal shifts. Vertical shifts and stretching. On the second form, it'll be, we'll add the k in the middle, which is going to be a horizontal stretch. And on the third, we will add the b inside, which will be a horizontal shift. Okay, so we'll add increasing complexity after we have a good understanding of what each function looks like. So let's start by taking a look at what each function looks like. So we have this page, and the first thing that we're being told in this page is that the functions sine and cosine have period 2 pi. And so that's what's being said in these two equations. It's saying that when you plug in a number into sine, and you add 2 pi to that number, it's the same as just plugging that normal number in. Same thing with cosine. Okay? So the big takeaway from this is that sine and cosine have a period of 2 pi. And just looking at these equations, what that means is that the graphs start to repeat themselves after 2 pi units, which is why the value at t is the same as the value at t plus 2 pi. All right, so let me write that down here and then say it one more time. So the period, the definition of a period, is how long it takes the graph to repeat itself. Oops, so how long it takes for the graph to repeat itself. And so we know that sine and cosine are based on the unit circle. We know that sine is the y value, are the y values on the unit circle, and cosine are the x values on the unit circle. And we know that those values, right, here's the unit circle right here, I'm going to refer back to this. The values as we go around the unit circle repeat themselves every 2 pi units. And that's because the unit circle is 2 pi, the perimeter is 2 pi distance. And so every time we go around 2 pi units, we repeat the same exact values. And that's why these functions repeat themselves every 2 pi units. And so let me write that down. So since the unit circle has a circumference of 2 pi, the values, the x and y values on the unit circle, repeat themselves every 2 pi units. And specifically, maybe units isn't the best word, they're radians specifically. The unit are radians. So every 2 pi radians, as we go around this unit circle, we see that the values are going to repeat themselves, and so that's why these sine graphs and cosine graphs repeat themselves every 2 pi units. And as we just look down here at these two graphs here, we can see that we're showing one period right here. We're showing one period of the graph because the graph starts to repeat itself right here. See how this is the starting point and it comes back to that point right here, and then it repeats itself again after that point. And same thing with cosine. Okay, so just to be clear again, this is sine up top, this is cosine down here, and we can see that cosine again repeats itself every 2 pi units. And so just looking at these two graphs before we get any further, this is one period. One period's being marked out from 0 to 2 pi, okay? And then another period would be from 2 pi to 4 pi. This is another period, because this also repeats itself. And another period right here. Now, I'll come back to this in a second. Let's not get too far ahead of ourselves. Let's understand the shape of the graph and why the graph looks like that. And so again, we've got sine and cosine being shown down here at the bottom page, and here's kind of a zoom in on what they look like. But let's take a zoom out on just sine and focus on sine and understand why sine looks like this. So let's notice some characteristics about it. So we know sine are based on the y values, right? Let me just write that down. When we want sine of t, this is from a previous class, we think about the y value on the unit circle. That's a key. It's a key to us understanding a lot of trig as we're relating everything back to the unit circle. And if we're talking about sine, that means we're talking about the y values on the unit circle. So let's look at this unit circle. And if we're talking about the y values, notice that if we start at 0, the y values increase to 1. Right, this first piece of the graph where the y values increase to 1, I'm just going to kind of highlight it here. Yours may not be in color, but mine, I'm going to try to make in color here. Let's make these lines red. These lines are getting taller because the y values are getting closer to 1. That's this graph. This is sine. That's this part of this graph. See how these lines are the same height? So the y values start at 0 because they start at 0 over here. And as the y values increase here, the graph of sine increases. But then at this point, the y values start to decrease. And so that's this part of this, on the graph on the right, where these y values start to decrease. So I'm going to just highlight these in blue, just to be clear about that. The y values then start to go down on the unit circle, and so the graph of sine starts to go down. Okay? And it hit its peak at 1. Of course, we know the max is at 1, right? So the y values went up to 1, and then they went back down to 0. And that's why this graph of sine goes up to 1, and then back down to 0. And then, if we're thinking about the y values still, the y values then go negative to -1, right? This is -1 down here. And then the y values increase back to 0. And so that's this piece of this graph, where the y values go down to -1, and then increase back to 0. And so let me just highlight that again on this. That would be like this line. These lines are now going negative, and so these lines are going negative to -1. And then these lines go positive. I'll do it with this. These lines go back from -1 to 0, and so that's why this piece of the graph goes from -1 back to 0. Now, let's notice some of the characteristics. Oh, and so let me just say that this graph here is just showing one period of pi, right? So one period of pi starts at 0 and it goes, one period of sine starts at 0 and goes to 2 pi. So this is one period of sine of t. Okay, and we can see that it has its 0 at pi, and we know that the point's pi right there because the 0 is at pi right here. The y value is 0. And so if this is just one period between my hands, it's showing us just this first period right down here. So I'm connecting the dots back to this bottom picture of sine, and we can see that what's in between my hands right here on the bottom, let's focus down on this graph, what's in between my hands down in this bottom graph is what's being shown up on this graph. Okay, so just know that this graph up here keeps going in both directions. It keeps going to the left and to the right, as is shown right here. Okay, so the periods continue in both directions. And so this graph keeps going. It goes out to the right and to the left. It just keeps going out, out, out. And you can see that we have a period here, we'll have a period here, we'll have another period here, we'll have a period here, and it just keeps repeating itself over and over and over again. And just as a reminder, just like, you might be thinking, like, why the heck do we care about this function anyway? Why do we want a graph that just repeats over and over? We use graphs like this to model phenomena that repeat. For example, the rising and the setting of the sun can be modeled using trig functions like sine and cosine, right? You can imagine this is the sun going up in our skies here in Fitchburg, and then it goes down, and it goes behind the other side of the Earth, right? And now it's going, and it's rising on the other side of the Earth, and it's setting, and then it rises again on our side, and then it sets, and it rises on their side, and it sets. And that process repeats itself. And so we can use functions like this to model those behaviors. And those behaviors and those types of phenomena happen a lot. Another example that I may have mentioned before is population dynamics. So interactions between foxes and, say, foxes and rabbits is a really good one. You can model that with sine and cosine. So follow my pen with this. Let's pretend that this is a fox population on the top, and this is a rabbit population on the bottom. So you can see the fox has a low population, the rabbit has a high population. Since there's a lot of rabbits down here, the foxes can eat, and the foxes' population increases. As the population of the foxes increase, they eat all the rabbits, and they decrease, right? And then as soon as there's not enough food left, the population of foxes decreases. But when the population of foxes decrease, there's no predators, and the population of rabbits increases. And so the dynamics, the interplay between increasing and decreasing, we can see in populations in the real world as well. Okay, so just trying to motivate like why we care about these graphs and what kind of phenomena we might think about modeling with these. Maybe you can think of one yourself. I encourage you to try to think about something in your own life that kind of repeats itself over and over, and what could we use to model that, what trig function could we use to model that with. So we talked about sine. I'll just say again, sine are the y values on the unit circle. The y values increase, decrease, become negative, and then go back to 0. And this is what is kind of a close-up of what's going on in the sine graph. So this is one period of sine you can see that's being graphed here. And you can see that it's got all the pi markers on it from 0 to 2 pi. Right, so pi over 6, pi over 3, pi over 2. These increments, these increasing increments, are the increasing increments around the unit circle that we've been practicing. Let's take a second to focus on cosine too. So if we're talking about the cosine graph and we're relating it back to the unit circle, so this is showing cosine down here. Okay, we've got cosine on the bottom. And they look very, very similar, but they're slightly different. And that's because cosine depends on the x values. Right? Cosine are the x values on the unit circle. So let me just write that down here. When we want a cosine value, we think about the x value on the unit circle. And so if we look at this unit circle and we think about the x values, we start here and x is 1. And then as we go around the unit circle, the x values get closer to 0 until there's 0 right here. And then they become negative, right? And then the x values go back to 0. And then they become negative. Yeah, sorry, and then become positive back to 1. And that's what's going on when we look at this graph, right? Let me trace it out with both. If we start here on the unit circle, we're starting right here with this graph down here. And as the x values, so the x values start at 1 and go down to 0. So they start at 1 on this graph and they go down to 0. And then the x values on the top, on the unit circle here, become negative to negative 1. And you can see down here, they become negative to negative 1 at pi. And then as we move to over here from pi to 3 pi over 2, the x values go back to 0. And so down here, they go back to 0. And then the x values on the top here go back to 1. And you can see it on the bottom graph, they go back to 1. And so this graph, if this is one period of sine, this is one period of cosine. And you can see that they don't look the same like this. I know when you kind of compare these two graphs, they look very similar because they both have a wavy pattern. But when we focus on just one period, which is what's being shown here, they're opposites of each other in some sense, right? When sine's 0, cosine's 1. When cosine is 0, sine is 1. And so they're translations of each other. They're shifts of each other. If we shifted sine over, it would look like cosine. Or if we shifted cosine over, it would look like sine. Right? Because when we think about going around the unit circle, the x and the y values are all the same. They're just in different order. They're just shifts of each other. Okay? And so again, just like we see repeating periods of sine, we have repeating periods of cosine. Here's one period of cosine between my two hands, right? So this period right here, that's one period. We've got another period on either side. This is one period over here, period. This is one period over here, right? You can see that the graph is repeating itself in each one of those pieces. And so we just see those repeating periods over and over.
So you know the building's going to lock at like 10:30 tonight?
Okay. And so in case it wasn't clear, what we want to do based on this page is we want to use these pictures as references when we're doing transformations. And so I'm just going to write that down just to be very, very clear about that. We want to reference these pictures and all the information we just learned about them when we're doing transformations. So reference these when graphing transformations. Oops, graphing transformations of sine and cosine. And so with that in mind, since we want to reference things when we're graphing sine and cosine, let's write down a few of the characteristics of each graph. Because when we do transformations, if we move the graph up, we want to know where the new max and mins are. So we need to know where the old max and mins are, right? If we shift something to the right or to the left, we might want to know where the new intercepts are, and so we need to know where the old intercepts are. So let me just take a second. Let me see where I can squeeze this in. I'll try to squeeze it in the right here. I'm going to squeeze in something here for sine, and then I'll write something for cosine down at the bottom here. Okay. So for one period of sine, we get the following. Notice that there's a min at 0, and there's a max at 1, right? That's because the smallest y value is 0. I'm sorry, let me start over. We get a min at -1, not 0. There's a min at -1 and a max at +1. That's because the smallest y value is -1 and the biggest y value is 1, right? And so for one period, we have a min/max at y equals ±1. All right? The min, right, so the -1 part, this low point on the graph, this low point, you can see it occurs at 3 pi over 2. And that's because this point right here, where the -1 y value is at the point 3 pi over 2. And the max is up here at 1, and that occurs at pi over 2. And we can see that on this graph. So notice that the max is at pi over 2. Okay, so let me write that down. So the min is at t equals 3 pi over 2. And the max is at t equals pi over 2. Again, that's because that's where the min and the max y values are. Let's look at where the intercepts are. So the intercepts are here, the x-intercepts. The x-intercept is here, here, and here, right? It starts at 0, it comes back to 0, and then it comes back and hits 0 again. And it happens when all the y values are 0. So the y value of 0 is here, here. These are the two places where the y value is 0. And that's t equals 0, t equals pi, and t equals 2 pi. And so that's why we have a 0 at 0, we have a 0 at pi, and a 0 at 2 pi. Because again, the sign is the y value, and that's where those y values occur. And so the x-intercepts for sine are at t equals 0, t equals pi, and t equals 2 pi. Okay? And again, we want to know that information because when we shift it around, we'll shift the intercepts and or the maxes and mins. Okay, so we want to know where those are. Just going to pause it just 1 second here and make sure you're caught up with that. For one period of cosine, I'm going to write that down here. Okay, so we're going to write down that same information for cosine. So for one period of cosine, we see that the min, again, is at -1 and 1. Right, the min happens down here at -1, the max is at 1. And again, on the unit circle, that's because the biggest x value is right here at 1. That's t equals 0 and 2 pi. And the smallest x value is right here at -1. That happens at pi. Right, and so we can see that happening here. At pi, we get the smallest x value, and then at 0 and 2 pi, we get the biggest x value. And so we have the same min and max at y equals plus or minus 1, but the locations are different. The min occurs at t equals pi, and the max occurs at t equals 0 and 2 pi. Again, just think about where the x values are on the unit circle. Cosine are the x values, and so when we're tracing out the x values on this thing, it's tracing out this cosine graph. The intercepts, we can see the intercepts occur right here and right here, so that are where the x values are 0. Right, the x values are 0 on the unit circle at right here and right here. Right, those two places are the two places where the x value is 0. And that occurs at pi over 2 and 3 pi over 2 on the bottom. And so that's where the x-intercepts are for cosine. So the x-intercepts are at t equals pi over 2 and 3 pi over 2. Again, that's because that's where the x values are 0.